So the first example I would like to take, if you have any field f be any field, then any n tuple structure like means n tuple space Fn is forms a vector space over this field F. So this F can be anything, like F can be R, the set of real number, or F can be C. In case if you think F is R or Rn, then it will be like this. This is the case. Similarly, you can define Cn. Now, what we need to prove? The addition and multiplication, if we define them component wise, these form a vector space. How to show it? Like we can show that if we define two vectors like x and y, you can also write this belongs to both of them, then if you try to perform, you will get so it is clear that if you define the sum in this way, then this addition is, you can check it is commutative. Like I have forgotten to mention, actually I'll be in some time, I'll obviously discuss about it, that a vector. So here it is, the addition is commutative. Actually normal way to define vector space is that like mathematicians prefer to define it like vector space is an abelian group. And abelian group, you can simply just hit Google and find out the means how to define the algebraic structure group or group in algebra. So you will find that defining group is not very complicated, and if a group, any operation in group becomes commutative, then we start claiming that the group with, actually as I mentioned in my earlier means first lecture on vector space, that we define like this inner element operation. Like if you consider this plus, this is actually an inner element operation. You are operating, or means this binary operation takes two operand from your set like V, or here if it is you want to call it Fn, it takes the two n tuple from your set of all n tuples and perform the operation on them, and then produce an element that is also a member of that particular set. Your set of all n tuples, the product result what we are getting it is the also an n tuple set. So this is actually an inner operation, and this inner operation is also a binary operation. It's operating on two operand, and now here one thing you can see that if it is by group theory, what we can say that if we find that this operation is commutative, then we can say that this group is an abelian group. Abelian group we will later on also in our control theory we will several times we will apply the concept of abelian group in different aspect. So I will discuss them later. So here also you can understand simply that this x1, x2, xn can be anything, like this can be 1, 2, 3, this can be minus 3, 4, 1, anything. Now if you add, whether it is the order of addition x1 plus y1 or y1 plus x1, it remains same. So it is commutative. Now you can also check if you pick up another z, like z is also an n tuple, then you can see that z is equal to z1, z2, zn, then you can find out that it is an associative property, like it is very easy to prove that. Right. Now existence of the additive like additive identity or the zero vector is also very easy for us. We can show it without any difficulty. So there always exists a zero vector. So what would be the structure of that zero vector? It would be like 0, 0, 0, n number of zeros, order tuple of n, and obviously for x belongs to fn, or in our case it is v or rn, whatever, you will always find there exists minus x belongs to Rn, right? Now similarly you can pick up a scalar. This is like the multiplication when we will consider. In short we can write it like if C belongs to F, then Cx should belongs to Fn. So it is you can easily verify it, like for R, if you want to verify, like C belongs to R and this is Rn, obviously you can get it will give you a structure like like x1, x2, xn. So it is easy to show that it will give you cx1, cx2, cxn. Now the other property, like you can easily prove, and you can try to means see the other property, like all other three related to multiplication is getting satisfied by the way we are trying to define it or not, and then you can also be able to draw a conclusion that this will form a vector space, like any field R to the power n forms a vector space over R. Now let us consider M cross N matrices, what would be the nature? If you consider it is R, it will be R M cross N, where M and N are right. So this R M cross N be the set of all M cross N matrices over your field capital M. Then we can easily prove that the sum of two vector, like here, what is your vector? Vector is the matrices, right? Now it is your duty, or if you fail, you should come to me and ask me that how in our conventional means when we are means just primary level physics, we used to teach that vector is something that is having uh, direction and magnitude, like magnitude and orientation. If quantity is having magnitude and orientation, then it is a vector quantity. So here in case of matrix, you have to figure it out. Like I can, the way we have defined the plus or this means addition, that inner operation addition and the outer operation scalar multiplication, we can always prove that the set of all M cross N matrices form a vector space over your field F. But here we are defining the things in this way. Like let me give you one example. If you take a 3 cross 3 matrix or for 2 cross 2 matrix, because or take any arbitrary one, A1 2. So now if we do this, it will result in A11 plus B11, A12 plus B12, A13 plus B13, so on, A21 plus B21, 22 plus B22, 23 plus B23. So item wise addition I am talking about. The way I have defined this in means, as mathematicians are laconic, they used to spend only a few lines and they would prefer to write it like in this way. Both are same things, and product C so product of them is defined in this way. They also form a vector space over the field. Now you may ask me, or confusion may come, that why Sayer is asking to verify or rather not verify, rather to corroborate it with our normal school level physics concept that vector is something that is having magnitude and direction. So if you have a problem, what means, let me just give you one small hint. For n tuple, you can easily verify it. If you have an n tuple in your, or let us take two-dimensional space only. So if you have a tuple here, say 2 comma 1, then obviously it means it is 2, in this direction it is 1. So you can always find out the way we have defined. If the norm you can, or the distance if you can define, then that distance will give you the magnitude and this angle will give you the orientation. So either you say 2 comma 1 or you say it like root 5 and angle tan inverse half, like this root 5 angle tan inverse half, as all of you are from electrical engineering, this also gives you an impression of a phasor diagram. So obviously that kind of arrow will diagram of arrow will evoke in your mind. So this you can understand that 2 comma 1 and this arrow, basically both of them are pointing, means are like they are almost the same thing. Now my question is that can we have this for matrix, can we have such kind of picture, such kind of geometrical interpretation, or if not, then what should we do, or how we should convince us that whatever is true for a pointed arrow, that is same is for tuple, same for matrix. Like in my first lecture I discussed that it is the idea of this axiomization of vector spaces to generate the idea of linearity. So how all this we can connect the dots between them, that we need to find out. Now let us take one more example. The space of function from a set to a field. What I am trying to say? Let A be a set of sorry. If B is the field and S be any non-empty set let V be the set of all functions from the set S into F, and furthermore we define the addition of two functions in this way, like addition of two function and we found that this Fs plus Gs also belongs to V, and if we pick one constant C belongs to F, then we can show that C of F of S is defined as CF of S is defined as C of Fs. Then with these two definition, V, the set of all function that maps from set S to V, set S into F forms a vector space. So if you find this description too abstract, let me help you by giving a more realizable example. Like we can define this function set V . So what is my objective here? So can you just identify what is your S? Your S is capital S is 0, infinity, and this R is like F is defined as it is a function that maps any element from 0 to infinity to R into R. Now the question here is that, like if you have already lost the interest in this subject, let me tell you one thing. If you apply your little bit of common sense, you will find that this is quite common in our control system engineering. In control system engineering, any state is what? A state is a function of any, if this is your state vector xt, what is how to pick up the value of t? T you should pick up from this set S, right? T always belong to this set. So x of t is any state. You can conceive that state vector is a function, that here obviously this one I am considering one dimensional. Suppose you are having only one state like x1t that maps you to like you can define x1 is a function such that there is no harm. Actually, you are this is the case. So I hope this one is convincing enough to means inspire you, kindle you to learn this linear space, linear algebra, so that we can apply these tools as per our own convenience. Now here one thing I forgot to mention in the previous case, that is the difference. Here try to understand the difference in your left side and right side. The difference in your left side, what that plus sign of this left side indicate? This one, what does it indicate? It indicates that means addition of function at each particular point, like you are adding x1 and x2 at each the particular time point, then that should be defined as a point wise addition. Like your x1 is having a value, say how to tell you the value of x1. Okay, let us consider x1 at certain time is having value -3. At that same time, x2 is having a value +4. So x1 plus x2 at that particular t, the observation time is -3 plus 4 is equal to 1. That is the way we are trying to define it. Then only it will form a linear space. And perhaps now you are getting the idea that how we can consider it is vector space, like so what I was trying to tell you, I just got this. It was some other things come in my mind. Anyway, so we are trying to define a pointwise addition, and if you consider this one, this is actually basically it is indicating a kind of amplification of your state, right, by a certain constant value. Now another example we can take, that the space of polynomial function so that space of polynomial function over a field f. So if a function, any form of function, so by intuition also you can find it out, or like you can think that okay, let me write it, otherwise you will get confused. Let f be any field rule of the form, like where your C0, C1, Cn are fixed constant and they all belongs to F. Now this polynomial function, this way we can also means just extend the idea of that example 3 here to find out that this is also a vector space. Now another example that is very important for us, like a space, example 5, that is the space of all solutions of an ordinary linear differential equation considered over form a vector space so linear ordinary linear differential equation. What we have again reached to the end of the page. So linear differential equation can be anything, like you can have any say this is a homogeneous differential equation. Now if you try to find sorry, here you should write x. Yeah. So if you try to find out its solution, then you will get, it is like, you can write it like if you define d dt is equal to p, then it is summation of, you can write it a naught, which is 0 in 1 is in this case, that p it is summation of pk x it is summation of right, a n minus k pkx is equal to 0. So this will give you what? This will give you a solution. Now a solution can also be viewed as a function over that semi-closed interval 0 comma infinity. So now probably you are getting that why the solution, when we are taking the solution and trying to plot for a two-dimensional system, why we are calling that phase plane as a it is a vector diagram, like vector. Why they are vector? Because your solutions are vector. Solution all solutions, they form a vector over your space. Now let me find some more. Now we will take some example where it is not a vector space, because otherwise you will think that that is trying to convince us that whatever we see or whatever we get in everyday life, everything is a vector space. It is not the case. Let me show you one simple example. Where it was, I just worked on my copy. Just a minute, huh? Like what I want to claim here that it is our observation that like if you have something subset of a set cannot form let me write subset of a field better. Like let me give you one example. Like if you consider the set of all rational number just a minute. So the set of all rational number q, if you check it, q forms a vector field over q. But if you take q and try to check that whether q forms a vector field over f or not, sorry, over r or not. Like what I am trying to say, that you are having q. Q is also, you will find that in set of all rational number, it complies with the requirement of the means for operation related to addition. Like what we know that in order to become a vector space with respect to addition, this means addition must be it is commutative, means that abelian property. The abelian means the tendency of abelian group to have a commutative binary operation. Commutative, the addition should be commutative. Then then existence of additive and additive inverse. So Q form a vector space over it. So, however, if you consider Q is a vector space, but you will see that even the Q forms a vector space over itself. But if you pick up, say, root 2, like if you want to verify whether Q is a vector space over R or not, then while picking up and consider means while you are trying to just verify the closure with respect to scalar multiplication. Scalar multiplication means you are picking up any scalar from the field R and you are trying to multiply it with the element of Q and see that whether the resulting element still a member of Q or not. So if you pick up, you must agree that group 2 belongs to R, and if you pick it up and say any element Q1 belongs to Q, and then if you do this scalar multiplication, then root 2 Q1 will not become a member of Q. So we can say that Q is not a vector space over R. However, on the other hand, it is true that R forms a vector space over Q. So let me just simplify what I am trying to say, that if you have two field, or rather not two field, also you can say that two simple abelian group, and one is a proper subset of other. Like here Q, you can say Q is a proper subset of R. Whatever element is present in your real number set, all the elements are not present in your rational number set. Obviously the set of all rational numbers like R complement Q is not present there. So in Q you are only having the rational numbers. Now Q is a proper subset of R. Both of them are having that nature, that addition. If you define the addition in a like addition is a commutative operation in both the same field. So you will see that Q is not a vector space over R, while on the contrary R forms a vector space over Q, right? So with this, let us move to the notion of subspace. So what is a subspace? Try to understand the difference between subspace and subset. All the subsets are not subspace. Let me give you one example. Let us take this xy and so this xy forms a vector space over the field R, like this two-dimensional vector space. You can represent this as a set of all ordered in tuple x comma y. So this set of all two-dimensional tuples. Now here, if we take this area, only the first quadrant, we can write any x is in this area is. Now, if you see that in this area, obviously the addition is commutative in nature. Addition is associative also. Additive identity also exists because 0 is also a part of your subset, but due to non-existence of your additive inverse, this subset cannot earn the tag or that epoch of subspace, right? It fails to comply the itself with the notion of subspace. So let us write the formal definition of subspace. let V be any field, V be any vector space over the field capital F are non-empty subset W of V is called subspace or linear subspace or a vector subspace of V if W itself be a vector space over the field F with respect to the same composition as defined for V. So if you defined it for V for like plus and addition as an inner operation and means a scalar multiplication, then for this case also you have to maintain that and check whether with respect to that two operation your subset W forms a vector space over the same field F or not. If it forms, it can form, then we consider it as a like a vector subspace of V, right? So what we can say moreover that if W is a like if W is different from V, then it is a proper subspace. Obviously, we know that W is a subset of V, and there is no way that W can have more elements than V. Only thing is it's possible that W is having elements that are not present in means W doesn't contain the elements that are present in V. So W becomes a proper subspace, right? So in this context, what we can say that we can define a few theorems, and the theorems are very necessary for us. So theorem 1. These theorems are available in any good book of linear algebra that states the necessary and sufficient condition for a non-empty subset W of a vector space over F of V is that W, basically we are looking for the closure. W is closed So how we can prove? It can be proved in a very easy way. Like F is a field. So if you think that your 1 is be the unity element of F. So if 1 belongs to F, then it implies now if you take a vector alpha belongs to W, then under that closure of your scalar multiplication, it will imply that minus 1 alpha will also belong to W. So that implies minus alpha belongs to W. So for any alpha belongs to W, you are having its additive inverse present inside it. And if the additive inverse exists, then if you add them, then you will get the zero vector like minus alpha plus alpha will give you the zero vector, right? So that we can prove that W is closed under vector addition, and the zero vector also belongs to W. So and being a subset of like of our V, why I am showing this means two only, like only the means existence of additive inverse and existence of additive identity, because being a subset of your original set V and V being the vector space, V implies that here the means addition is always commutative and associative, and being a subset of V, W inherit all this from V. Only we were worried because we were means not sure, means, or rather the only question mark that can means question that can be raised in this context is that whether the additive inverse exists or not. Like the example I just discussed in the very beginning of subspace, where it is here. Here also you will observe that the addition was means commutative and associative, but due to, as well as the existence of additive identity was also there, but due to non-existence of additive inverse, this subset fails to qualify it as a subspace of the two-dimensional vector space. So this is the condition you must have acquainted with the use of all those tools. Anyway, so what is the important theorem here is that the same condition for a non-empty set W, non-empty subset W of a vector space V is over the field F is, if alpha comma beta, this is very important, and you will after I write the complete means equation, you will find its means you are quite familiar with this equation or expression rather. Sorry. It should be comma alpha beta vector. So basically it is showing that W is closed under vector addition and scalar multiplication. So in your linear system theory, when we study superposition from our childhood, we try to mug up things like superposition is like additivity and homogeneity. So if a function is means obey a superposition principle, then we can show that suppose if a function f is linear and it obeys, obviously it has to obey superposition principle, then f of x plus y is equal to like f of x plus f of y, and f of cx is equal to c of fx. We call one as this one as homogeneity and this one as additivity. You perhaps means read all these 1,000 times during your undergraduate course, once during circuit theory, another time means once again during control theory. However, in a nutshell, you can write it like if you have it like it will give you something like, obviously x and y are variable and c and d are the constants. So now my question to you is rather quite simple. That in while writing superposition, why people always mention this additivity and homogeneity? And why? Let me explain one thing. That f of say x plus x, that gives me f of x plus f of x is equal to 2fx, and here also this can be written as f of 2x. So why not uh, can't I claim that additivity implies homogeneity? Why do we need to mention homogeneity separately than additivity? You must know the answer. And if you do not know, you must try to find out the answer from your book or anywhere else. Or a simple analysis can give you the answer. But you have to think that why we mention always that it is additivity and homogeneity. So this is another question. One question I asked, that how matrix can be can mimic pointed arrow type things, or at all they can mimic or means can give us a representation like that kind of pointed arrow or not. And this one is the second. So I expect that during our next class you must discuss this with me. Obviously, if you find it interesting, otherwise it is of no use. Now, one thing I would like to means instead of proving this one, I would like to discuss another few examples just to means we can prove this also, that last one what I wrote here is now. Okay, let me prove it, because at least trying to understand the proof also make us means improve our orientation towards mathematics. Like, what was the claim? That basically we want to prove that if A, B belongs to F and alpha beta belongs to W, then if A alpha plus B beta belongs to W, then that is closure under this is also gives us like necessary and sufficient condition to claim that W is a subspace. So first let us prove the necessary condition, because most of the time we fail to achieve the necessary condition in our life also. So A belongs to A and alpha belongs to W. These together implies that being a subset of V, this W, like it has to be like okay, so it implies A alpha belongs to W. and also A alpha belongs to W, and if B belongs to F and beta belongs to W, then it implies B beta belongs to W. Right? Now A alpha belongs to W and B beta belongs to W, then both of them, as in order to comply with the requirement of subset, subspace, they must make sure that A alpha plus B beta, this also belongs to W, right? So A alpha plus B beta should belongs to W. Now this condition therefore is necessary. So first what we are trying to do, this is a closure under scalar multiplication, this is also a closure under scalar multiplication, and then it is closure under addition. So if that is the case, then what we can prove that let W be a non-empty set, subset of V satisfying that. Now we are trying to prove the sufficient condition. So we know that W be a non-empty subset of V. It satisfies the condition that A alpha plus B beta belongs to W. Right? Now we take A is equal to B is equal to 1. Then what we will get, that if alpha comma beta belongs to W, then it implies 1 alpha plus 1 beta, that also belongs to W, and hence alpha plus beta belongs to W. Now if alpha, because why this is so? Because all alpha beta, they are the element of V, so they inherit all the properties of V here. Now if W is closed under vector addition, we can take A is equal to minus 1 and B is equal to 0. So if we take that, then what we will get? We will get that alpha belongs to this during proof, if we need to change the page, that is quite inconvenient. So it is sufficient. What we are observing here, that if A is equal to minus 1 and like B is equal to 0, then we will see that there is no harm to means nobody can stop me for adding one means doing it like A alpha plus B alpha. I am not obliged to consider always that alpha and beta are different, right? Alpha and beta both should belongs to W, but there is no such obligation on me that we have to select alpha and beta different. So I can take alpha and beta, they are same. So if we take them same, then what we will get? We will get it like that if alpha and beta they are same, then we will be getting this belongs to W, and in following steps we can write. Now 0 being the additive identity, see there is a difference. This one is 0 is a constant with a vector alpha, and here it is not the scalar 0, rather it is a 0 vector. However, being the additive identity, what we are getting minus alpha belongs to W. So that implies the existence of additive inverse, and if we take both A, B 0, then what we will get? Like we will get, if A, B is equal to 0, we will be getting there is no claim has been made like alpha A or B cannot be is equal to 0. So this belongs to W. Now this can be written like so here we prove that existence of additive inverse, and here we prove that existence of additive identity. Again and again I am telling you that other two property of addition will be automatically inherited because your W is a subset of V. So if addition is commutative and associative operation in V, then it will be similarly commutative and associative in W. However, what we need to search or to ensure that existence of additive inverse and additive identity. Here we can prove that this existence, the additive inverse as well as the additive identity exist for this. Now, obvious question that comes in our mind, then what is the smallest subspace of any vector space? Can you means give me any answer that what would be the smallest subspace? Like what means could be a very small subset of S.